All right, this was a question on the quiz. What is the pH of a solution prepared by adding hydrochloric acid to ammonia? You have two things in your beakers, and you'll recall from our flow chart, once you have two things, what we always find out they are is an acid and a base. So let's work down through it and make sure we understand how that works. Hydrochloric acid is HCl. That is indeed an acid. In fact, it is a strong acid. Ammonia is NH3. You should be familiar with both of those, and ammonia is a base. Indeed, it is a weak base. Those are all facts about those two that you should be familiar with. So, I have an acid and a base. And that is always how it will end up if we have two things and it's a what is the pH of question. So I've got my acid and a base. The next question after I identify the acid and the base is to ask myself, are they conjugates or not? And these two are not conjugates. Again, that is a chapter 15 kind of thing that you still have to be familiar with. These two are not conjugate acid-base pair. And since they're not conjugates, then how do I work that? I run a chemical reaction. This is a reaction between an acid and a base. We have those reactions back in chapter 5 if you need to review them. An acid plus a base yields a salt plus water. It is a forward reaction. It is not an equilibrium reaction. It is a forward reaction. And in the case of having ammonia or a blah blah amine base, you won't actually get the plus water, you'll just get the salt. Recall from chapter 15 that the Bronsted-Lowry acid, which HCl is, will donate an H plus to the Bronsted-Lowry base, which is what the NH3 is. And so you essentially end up with the chloride ions after he donates that H plus and the ammonium ion after he receives the H plus. Well, this is the salt that you get. Acid plus a base yields a salt plus water. We almost always write the plus ion first, so this is ammonium chloride. But we know from this chapter that once we get our salt, we have to break it up into ions anyway, so I'm going to look back up here at the ions that I wrote. So HCl and ammonia react, I get the chloride ion and ammonium ion. So I'm going to leave it like that. All right, I got myself a little space here. The next thing I need to do, this is a reaction, so I've written the reaction. Now I have to run the reaction with the numbers, and this typically ends up being a limiting reagent type problem. It is a completely forward reaction rather than an equilibrium. So it's kind of like an ice table, but I have an initial change and a final amount. It's not really an equilibrium down here because this is going to proceed in the forward direction. As suggested in class, it's probably best to run this in moles rather than molarity when you do your stoichiometry. And here's how I get the moles. I have milliliters and molarity is equal to moles over liters. So I'm going to solve for moles by taking molarity times liters, and I'll do that for both the ammonia and the HCl. I do need to worry a little bit about significant figures. My calculator gives me just these numbers. There are some zeros on the end. It looks like both of these need 2 sig figs, but I'm just going to write them for brevity's sake as 0.01 and 0.03, but recognize there are 2 sig figs on there. All right, these guys are 0. This is a limiting reagent problem. I have the least amount of HCl, which means this reaction is going to proceed until all of the HCl is gone. It is a 1-to-1 stoichiometry, so it will proceed until all the HCl is gone and 0.02 moles, this is in moles, of ammonia is left. I can't stop there. I have to think about the products, and the products are forming, and because of the stoichiometry I get 0.01 moles of each of these. But recall that the ion Cl minus is neutral, so actually I can ignore the Cl minus. So at the end of this limiting reagent problem, I have 0.02 moles of ammonia and 0.01 moles of the ammonium ion. I have 2 things left in my beaker when this reaction is done. They are ammonia and the ammonium ion. These are the only 2 things I have to keep track of. Ammonia is a base. It was from the very beginning. And the ammonium ion is the conjugate acid of ammonia. Ammonium ion is an acid. I have a base and an acid are the 2 things in my container. I'm back to this kind of problem, and the next question I ask myself is, are they conjugates? And in this case, they are conjugates. And you will recall from our flow chart, if I have an acid and a base in the same container and they are conjugates, it is a buffer problem. You can use the shortcut, the Henderson-Hasselbalch equation, with this if you want to, but you can also set up an ice table. So let me get some space and we'll set up an ice table with this. Actually, let me just scroll. All right, we're back. So I have ammonia and the ammonium ion in an equilibrium system. Those are the only things that are left. For an ice table and an equilibrium constant, I do need molarities. And so the concentration of ammonia is the moles per liter. There are 0.02 moles. To get the liters, let me scroll back up because I've already forgotten. I have 10 milliliters of the HCl and 200 milliliters of the ammonia, so there is a total of 210 milliliters in my container. That would be 0.210 liters. Let me go ahead and set up the other and then I'll punch them in. For the ammonium ion, I have 0.01 moles. Alright, I'm keeping these numbers on my calculator because I don't want to round them yet. And I'm going to show you another little shortcut here in just a second. But I've got these stored in memory so I don't have to round them. So let me get some more space and then we'll set up our ice table. The way that we work a buffer problem is it is one equilibrium reaction, one ice table, one K value. I could either write the the Kb for ammonia. I could write the base reaction of ammonia since ammonia is a base, or I could write the acid reaction of ammonium ion since ammonium ion is an acid. And I can do either one and get the correct answer, but since the Kb table lists the Kb for ammonia, I'm going to go with the base reaction. If I go with the acid reaction, I would have to calculate the Ka from the Kb of ammonia, and so I would still get the right answer, but I'm going to start with the reaction of ammonia. Now I can write out ammonia, or I can write out the generic B for a base. So this is my equilibrium reaction. This is my ammonia, and this is my ammonium ion. These are my conjugate pair. And so in my ice table, my initial concentration of my base is 0.9523 ... Again, I've got those numbers in my calculator. The initial concentration of my BH plus is 0.047619 ... This is 0, and I've got some X's. And I set up my Kb value for ammonia, and Kb is 1.8 times 10 to the minus 5. I got that off the table. I'm going to go ahead and use the approximation that this plus X and minus X are small, so that I don't have to rewrite it over and over and over again. So I've got the BH plus concentration times the OH minus concentration divided by the NH3 concentration, and at this point I am solving for X. When I solve for X, I get 3.6 times 10 to the minus 5. I would like to point out at this point that these numbers came from converting the moles to molarity for each of these, and so each of them was divided by exactly the same volume, 210 milliliters. And then down here it was also a ratio of these two numbers, and so technically speaking, mathematically speaking, I could have jumped right on and used just the moles instead of the molarities. We can't use the moles in the equilibrium formula, but mathematically I would have gotten the same answer if I had used the ratio of the moles rather than the ratio of the molarity, because they're all in the same solution. And by the way, this is exactly what the Henderson-Hasselbalch equation does, is it takes that shortcut and it puts the shortcut in that you can use moles of each rather than molarity. But I get the same answer either way. So again, I've gone ahead and used molarity. I've gotten this value for X. Remember that X is the hydroxide ion concentration. Let me come up here. That means take the negative log to get the POH. The POH is 4.44. To get the pH, subtract that from 14. And the pH is 9.56. which is, I think, option D on your quiz. So that's how I find the pH of the solution that starts with hydrochloric acid and ammonia. I run the chemical reaction until something is gone. That's a limiting reagent problem. I figure out what's left over at the end. I identify what's left over at the end as being a conjugate pair. So at that point it is a weak, either a weak acid or a weak base problem. I chose to do it as a weak base.